Good morning. Good morning, everyone.
Good morning. How are you doing?
I'm doing great, thank you. It's a very beautiful day outside.
Mm-hmm.
Good morning, Kim.
Morning, how are you?
Great, thank you. And you?
Good. Can't complain. Beautiful day.
All right. Okay, everyone. Welcome back. Okay, today is 23rd. This is week 2. Of course, Tuesday. Okay, Tuesday. Yesterday, we talked about 2 to the power x. Okay, 2 to the power x, which is this curve, right? And the log base 2x. Okay, and we plotted the points. Input, output, input, output. Okay, we plotted the points. Oh, by the way, in the office hours, someone asking me about one of the questions on the quiz. Okay, so I put it here, right? This is actually related to the function f of x equals to 1 over x. Okay, and we're going to talk about another concept. Okay, so that's what we're getting to. Okay, so just don't do anything here. Hi, Lynn. Good morning, Lynn. Okay, so here I still want to recap on what we had done yesterday. Okay, we graphed the 2 to the power x, log base 2x, and we know they're inverse function to each other. Their domain and their range, and one's domain is the other's range. Okay, one's domain is the other's range, right? Domain range relationship. X-intercept, Y-intercept. We covered all of that. We covered all of that stuff. One more question, okay, I wish to introduce here is increasing function or decreasing function, okay? For this, I'm asking you to go back to page number 2, okay? There's a definition about increasing function definition, and I want you to take your time to write it down. Okay, increasing function, decreasing function. Decreasing function. We did a one-to-one function, right? We did a one-to-one function. Since we did one-to-one function, so when we look at the increasing function, decreasing function, and these two concepts are very, very important concepts in calculus class. Okay, you're gonna use it, and it will be introduced to you again, and you'll be using increasing function, decreasing function in chapter 4 calculus. Okay, we introduce it here because the functions in our consideration, a lot of them are increasing function, a lot of them are decreasing function as well. Okay, so here I want you guys to take your time to write it down. What is the increasing function and what's the decreasing function? Okay, the words, okay, write down the words. Okay, this is not very pretty. Okay, so let me copy from a Word document. So copy from Word, maybe a little bit better. Okay, So increasing function right here, okay, X function is called increasing. A function f is called an increasing function on an interval, okay, on an interval. So this time is not on the domain. One-to-one function is about, excuse me, one-to-one function is about function have those properties that, you know, on the entire domain. But for increasing function, however, it is on an interval, okay? It's very important to notice those differences. And we see the word whenever again. In the interval I. That's increasing function, okay? So take your time to write it down and think about what it is. Think about what does it mean, right? What does it mean? A decreasing function is a function All right, did you write it down? So two more concepts. So far we have introduced how many concepts? Function, one-to-one function, okay? So function, one-to-one function, increasing function, decreasing function. Four important concepts. How do we deal with these concepts? All right, we need to understand these concepts. How many concepts you're going to be dealing with? Many more in calculus. Okay, so this is just the beginning. You start to learn, you start to learn to study mathematics this way. Okay, really read the words, try to understand it, making connections. In calculus class, you're gonna be doing this all day long. Okay, you're gonna be handling many definitions, many theorems. Okay, one day I have a PowerPoint slide about those concepts. So how do you handle them? How you can make it, right? You finish this class, you get into calculus class, how are you gonna make it? You need to get out of that class. We are learning the way to handle those concepts. Of course, those concepts are much harder, much more interesting. So hopefully this way will help you to learn how to handle calculus. All right. Decreasing function, right? You may also want to recall one-to-one function, right? One-to-one function. These three definitions seems to rhyme in some way. Okay, shall we put the function definition of one-to-one function here as well? What's the definition of one-to-one function? just for the fun of it. 1 to 1. Is called 1 to 1. One to one. Okay. Whenever. All right. So these are the three very important concepts. 1 to 1, we studied. Now increasing function, decreasing function. So let's study one at a time, okay? We did 1 to 1, so that's being checked. Increasing function, what does this mean? What does this mean? Whenever one input is smaller than the other input from a particular interval, their output, their respective output also has this same relationship. Okay, also have the same relationship. Do we have a picture? Do we have a function that has that kind of property? Have we learned a function had that property so far?
Yes.
Okay, if you look at all 14 functions you have been assigned as homework. Okay, all 14 functions you've been assigned as homework. Any one of them you think will be an increasing function.
F of x equals to x.
Very good. Excellent. How about x squared? Y equals x squared.
Only for
That one would be
half
increasing
of
too.
it.
Sorry?
That would be increasing too, x squared.
X squared is increasing too?
Yeah.
Okay. So examples of increasing function. F of x equals to x. Very good. And the other function we were considering is f of x equals to x squared. Is that an increasing function?
Yes.
Think again. Okay, so how do we make the statement? How do we make the case that f of x equals to x is an increasing function? We're going to apply the definition, right? We're going to apply the definition. So whenever x1 is less than x2, and this time actually is in the domain, it's in the entire domain. Okay, f of x1 indeed is less than f of x2 because the output is the same as input, isn't it? Right, so that's a statement you can make because the output is the same as input. How about f of x equals x squared? Is this function increasing or not? whenever.
Oh, because x1 is okay, because yeah, never mind. Because x1 it has to be less than x2 and then to be able to equal that, right? So it can't be.
We're talking about whether it is an increasing function. Is it an increasing function? Is it an increasing function? What is the graphic feature of an increasing function? What is the graphic feature of the of an increasing function? Do you guys have graphed this function, right? So how does it look like? How does it look like? Everybody should be able to graph this one, right? I trust you guys have graphed this function. How do you illustrate that this function is increasing? Okay, so this is fine, okay? Whenever x1 is less than x2, okay? Suppose you pick a point here. That's x1, right? x1. And you pick a point here, x2. x2. Input, output. How long is x1? What is x1? This much is x1. It's a negative number, right? Or whatever. You can choose both as positive, right? Both negative, one is positive, one is negative, doesn't matter. And x2, what is x2? This is x2. They're all measured from the origin. They're all measured from origin. So x2 is larger than x1. x2 is to the right of x1 on the number line. Therefore, x2 is larger than x1, yes? And what are their respective function values? What's their respective function values? This is f of x1, and this is f of x2. And clearly, f of x1 is larger than, f of x1 is larger than, is smaller than f of x2, right? And this is f of x2. And this has to be true for any two x1, x2 you pick from the domain or a specific interval. Do you guys follow me? That's what whenever means. You have to, in your head, you have to run all possible x1, x2. And that must be true. And that makes an increasing function. Is it true for this function? Well, obviously it is true, right? Because the output is always the same as input. So when the input x1 is smaller than x2, the output, of course, is also x1 less than x2. That's a very easy case to present. That's a very easy case to present. But you can see x1 meaning is a horizontal measurement. F of x1 is a vertical measurement. You guys follow me? Basic, very basic, right? The basic thing. x2, f of x2. All right? That's the visual. That's the visual. Do you see it? Does everybody see it? Yes, X1 is the same as, the output is the same as input, but the input is a horizontal measurement. The output is a vertical measurement. Do you guys understand that? That's the basics. You probably have learned in elementary algebra. So this function, as we emphasize, this is a very important function. What does it say? It says the output is the same as input. Okay, next, let's look at x squared. Let's look at x squared. Okay, so I'm gonna clean it. Did you guys take notes? Did you guys take notes? I'm gonna clean it up. Okay, that was easy. How about x squared? Is it an increasing function? You guys have graphed it, didn't you? Whenever you say a function is increasing or decreasing, you have to refer to the definition. You also have to refer to an interval. You see, a function, it says increasing function is, a function is called an increasing function on an interval. You not only have to tell the reader what it is increasing or decreasing, you have to tell the reader where. Okay? For example, you say, oh, my grandparents live in Springfield. What do you think of that answer? There's so many Springfields in the United States, right? You didn't give a complete information. Do you understand what I'm saying?
Yeah.
You have to tell them, is it Illinois or, maybe another state? All right. So you when you tell if a function is increasing or decreasing, so a complete answer for this one is what? This function f of x equals to x is an increasing function where f of x is an increasing function in its domain. You have to tell them where, which state. Now let's look at x squared. That's f of x equals x squared. Is it an increasing function? Some of you said yes. Did some of you say no?
Yeah.
Oh, so we have yes answer, we have no answer. We know yes and no are opposite, right?
Yes.
All right. So if you look at the graph, right? If you look at the graph, everybody know the graph, right? That's the graph. Since everybody know, we're not going into details. I trust you guys have done the details. Okay. So here's the function. Increasing function or decreasing function? Well, you have to talk about where. If you talk about the entire domain, it's neither. It's increasing from 0 to infinity. And it's decreasing. We introduced the definition of decreasing. So let's see what's the definition of decreasing. So this function is increasing somewhere, decreasing somewhere, and neither on the entire domain. Okay, so let's put the wording correctly, and we're gonna look at the definition of a decreasing function. Okay, decreasing function. What does the definition of decreasing function say? Okay, so let me just put it here. So whenever x1 is smaller than x2, their respective output has a different relationship. Their output is the other way around. Or if this is less and this is greater. You guys see that? So let's look at this graphic. Let's look at the graphic. Okay. If you look at these 2 points, point 1 and point 2. Okay, so what is x1, x2? This is be x1, and the other one will be x2. That's x2. You follow me? x1 is smaller than x2. Do you follow me? x1 is smaller than x2. So this is x1, and the other one is x2. What are their output? Their output, this is f of x1, which is x1 squared, and this other one is f of x2, which is x2 squared. If you run all possible x1, x2 on this side, okay, from positive number or 0, from 0 to infinity, it is an increasing function, isn't it? Did everybody get that?
Yeah.
Yeah?
Yes.
Everybody get that?
Yeah.
So that illustrates that f of x equals x squared is an increasing function where my sentence is not complete. My sentence must be complete with all the information. So how do you make that statement? Right? We said it again, our student, a lot of them, they understand, they're very smart. But when they put on the paper, they lose all the points. How come? I hear that a lot. I understand everything you talk about in class, but how come I lose 10 points out of 12? Huh? You need to pour out what you know and put it in the right way. Okay, so how do we make that statement? Okay, for any x1 smaller than x2, you see, I'm quoting definition. I'm quoting definition. Or you can say whenever. Okay, you can say whenever, really. Whenever, or for. Okay, and you also indicate x1 is x1 comma x2 are non-negative numbers. What am I telling the reader? I'm telling the reader that x1, x2 are chosen from 0 to infinity. And there 0 is included, non-negative numbers. F of x1 is smaller than f of x2. That's a true statement. Okay, or you can add, you know, x1 squared, right? I'm going to write it better because this software doesn't allow me to type okay, properly. I'll write properly, okay? Okay, so whenever, so I'm quoting the definition, I give the reason why, and then I go ahead and says, thus, f of x equals to x squared is an increasing function on the interval from 0 to infinity. That's the complete statement with reason illustrated by definition. This is the kind of sentences, this is the kind of wordings you use in calculus. Okay, precise, where, why. You got it? Now, so I'm going to type it properly, okay? Did you guys have the picture? Okay, I'm going to write it down properly for you using the proper notation. Okay, so whenever x sub 1 is less than x2, and okay, x1 comma x2 belongs to certain interval, I have to tell them where, because the statement I'm making is not going to be true if I'm talking about the other interval. Do you follow me? 0 to infinity. Whenever x1 is less than x2 and x1 and x2 are both from the interval from 0 to positive infinity, x1 squared is less than x2 squared, x sub 2 squared. i.e., okay, why do I quote this? Because that is related to the function, right? I'm referring to the output. So f of x1, okay, f of x1 is less than f of x2. Okay, I want to make it absolutely clear to the reader. So your professor has no excuse not to give you a point. You understand? Okay. I'm sorry, look at this mess, right? So this is what we call the two software don't talk to each other. Okay, but I'm gonna just clean it up. Thus, f of x equals x squared is increasing. Where? On this interval. Okay. In calculus 2, chapter 4, you'll be studying, maximum, minimum, those concepts, and you're gonna be using these wordings, okay? Because the function is increasing here and then decreasing here, and therefore it reaches its peak, maximum. And your function is decreasing here and increasing, afterwards. You need to specify the interval, and then it reaches the lowest point. Local max, local min, you're gonna be using these wordings, trust me. Okay, if you use the exact wording I teach you today, you will get points. But if you miss some things here and there, you're gonna miss 1 point here, miss 1 point there. That's the reality. That's a reality, okay? All right,
question.
so, yeah.
Which statement would be better? The first one you wrote, like where it
This
starts
one.
off.
This one.
Oh, okay. But the other statement would be acceptable.
Sorry?
The first statement, would that be acceptable on the test?
The first one is fine but I didn't use the mathematical notation because Zoom doesn't allow me to type it that way.
Oh, okay.
Okay, so use this is the better. The box I put here is not the best, but because I want to keep the picture at the same time. You know what I mean?
Mm-hmm. Yeah, I know what you mean.
But I have limited space on the screen.
Oh, okay, yeah, you're all good, no worries.
All right, thank you for asking. So if you have any question, please do ask me, okay? Because I want to make it absolutely clear because it's about your point. It's about your points. I got my points, I graduated, right? You need to get your points and graduate, right? Is that right? Okay, so can you make a similar statement about decreasing? Right? Because you can clearly see this is decreasing, isn't it? This piece is decreasing, right? But this piece of decreasing obviously is from negative infinity to 0. Okay? So I'm going to copy this picture and we're going to make we're going to try to make a statement, okay? It seems that I know how to do this because I was a student before. I learned this stuff. You guys are new to this, so you're gonna probably have to struggle a little bit, right, to learn this. But I assure you, you will get the hang of it. You will get the hang of it. It just takes some practice. Okay, so that's the definition of decreasing function. And here we have a function. Okay, here we have a function, and this function is f of x equals to x squared. Okay, this function is it's f of x equals squared. And we can see clearly from the picture, it is decreasing from negative infinity to 0. How do you make that statement to describe it? In your calculus class, you cannot tell the professor, oh, look, it is decreasing, look. Okay, that doesn't count for any point, I'm sorry. You have to be able to make statements like this. Quoting the definition. Okay, so how are you gonna make it? Okay, so first let's understand why it's decreasing, right? X1, so you pick arbitrary 2 points, any 2 points. I pick a point here, and I pick a point there. Right? So what is x1, x2? X1 has to be smaller than x2. Right? Which number is smaller? The number to the left of the number is on the number line is smaller, right? So here you're going to draw x1, x2. Okay, so this is x1. Okay, that's how long x1 is. Okay, but what is x2? This is x2. Is that clear to you guys? And that's x2. Can we say x1 is indeed less than x2? That takes a little convincing, isn't it? Then you say, oh, x1 is longer than x2, isn't it? How come x1 is smaller than x2? Do we have a question like that? Do we have a question like that? Well, They're negative. They're on the other side of 0, okay? So if x1 is -5, x2 is -2, -5 is smaller than -2, yes? Does everybody follow me? If you wonder, if you're there wondering, x1 is smaller than x2. But let's look at f of x1, f of x2. What is f of x1? F of x1, so I'm gonna use the green color. This is f of x1. You follow me? This is f of x1. Okay, so the output is vertical measurement. Input is a horizontal measurement. They're all measured from the same place, yes? They all measure from the same level. Okay, f of x1. I cannot emphasize enough about these basic concepts. Okay, I couldn't tell you how many times I have a student in calculus 2. They forgot about this basic concept. And that prevents them from seeing what they should be seeing. Okay, so let's look at f of x2. This is f of x2. Okay, so this height, this green height, obviously is shorter than the other one, and they're above x-axis. That means they're not negative, they're both positive. Right? So now can we make these statements? Whenever, does everybody follow me? Whenever x1 less than x2 in the interval, this interval is going to be specific from -infinity to 0. I can include the 0 though. I can include the 0 though if you want. Okay, but oftentimes we use open interval. F of x2. Okay, so whenever we have this, okay, I want you guys to digest this statement. X is 1 squared is larger than x2 squared. That is, okay, you have to judge, you have to agree, you have to judge this statement is true, okay? I'm quoting it, but you have to judge this statement because whoever grades your work isn't gonna judge whether your statement is true or not. You follow me? Okay, this is f of x1, and this is f of x2. So this is just to quote the definition.
Professor, can the does the interval can it include 0 or no?
It doesn't really matter. Okay, in your calculus class, actually, you often consider the open interval. Okay, I could include the 0. Both are correct. Okay, if that bothers you, I'm gonna put it this way. The statement we make here are correct for both interval. Okay.
And I'm also a little confused on why x1 would be less than x2.
I'm sorry. Can you speak louder?
Yeah, I'm a little confused as why x1 is less than x2. Because like it's on the
because
graphic.
I choose them this way. Why x1 is less than x2?
Mm-hmm.
Is -5 less than -2?
Oh, okay. Never mind. I got it mixed up. All good.
Okay.
All good. Never mind.
And on number line, the number on the left is always smaller than on the number on the right. Remember number line?
Yeah. Yeah. So
Number line,
but then
the number on the left
like,
is always smaller than numbers to its right.
Yeah. Yeah. My bad.
Does everybody follow me? So you think of some examples such as -5 less than -2, but -5 squared is 25, positive 25, -2 is 4. Therefore, 25 is larger than, so the function is reversed. The output, the relationship is reversed. Does that make sense? But you cannot use those examples in this statement, okay? Otherwise, you fall in the trap of anecdotes to, using anecdotes to prove for general case. You cannot do that. You have to use this wording. You guys follow me? Whenever input 1 is smaller than input 2, the output for input 1 will be larger than the output for input 2. That's what it's saying. And I'm quoting the definition. It fits the definition. And then what do we say? F of x squared, okay, I'm gonna put it here, okay, is decreasing on the interval or in the interval -∞, comma 0. And here I'm just say because. Okay. So you tell the reader it's decreasing, and you also have to tell the reader where, okay? If I'm grading your work in calculus class, and you tell me, oh, this function is decreasing, you didn't say where, I will, when I grade your work, I will say where, -1, -2, so on and so forth. You guys follow me? If you don't tell the reader where, you're gonna lose a point or two. Do you follow me?
Yes.
Okay. I'm just telling you how your math nerdy professors function. All right. All right. So we learned 2 more concepts. Next, we have to go back to our exponential logarithm functions, right? We'll go back to our exponential logarithm functions. Okay, you're going to continue to study what else functions increasing, decreasing, because we don't have time to do this over and over again. Okay, so next. Okay, next, come back to our function 2 to the power x . 2 to the power x. Okay, 2 to the power x. Okay, we have two other functions. One is 2 to the power x. And the other one is log base 2x. Are they increasing or decreasing? And we actually know they're inverse function to each other. So let's give them a different name. Okay, well, we can even use this notation now, F inverse. Let's use that notation. Right, because yesterday we have acknowledged that these 2 functions are inverse function to each other. Right, we just studied the inverse functions. Are they increasing or decreasing? Are they increasing or decreasing?
I think 2 to the root of x, or not root x, 2 times x squared is increasing, and log 2x is increasing too.
Okay, so let me explain to how you read it, okay? This function, you will read it as 2 to the power of x. Okay, and this one you read it as log base 2x. They're both increasing, aren't they? They're both increasing, aren't they?
Yeah.
Right? How do you decide that? How do you decide that? First, how do you decide that from a graph? So let's do the graph and then we do the wording. So let's practice, right? I just show you something. I want you to practice this. What I'm showing you are very basic. Very basic. Why do I do these basic things with you? Because in my view, a lot of you struggle so much. It's because you didn't have the basic. You didn't do it. Because you didn't do it, the foundation is removed from your bottom. You didn't have the foundation. You built your whatever on the sand, not on the rock. You have to build it on the rock. This is a rock. Okay, what we're doing here is the rock. Right? You understand that metaphor, right? If you build your sand on the if you build a house on the sand, what's going to happen? Yeah. Okay, this is 2 to the power x. Okay, I can make some adjustment. Whenever, so decide whether it's an increasing function, you just have to do what we just did. You choose any 2 points. You choose any 2 points. Okay, point 1, point 2. x1, x2. x1 is smaller than x2. Arbitrarily, okay? From this point forward, you guys have to know how to express arbitrarily without using examples, okay? But in your head, you run through all possible cases. You run those cases in your head or on your scratch paper. But in expression, when you say yes statement, you have to be able to think of all those cases and make a general statement. And you call this abstraction or not, this is abstraction. But that's what is required to be successful in Cal. You have to be able to extract general statement from the special cases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever. Okay, so x1 is smaller than x2, right? What is f of x1, f of x2? That's f of x1. Wait. This is f of x1, and that's f of x2. You follow me? This height is f of x1. You see, after doing all of these things, The visual, the words, do you see some consistencies here? We're actually doing the same thing over and over again, just for different rules, don't we? Do you guys see that? We're doing the same thing over and over again about input, output, input, output, input, output for different rules. Do you see that? Do you guys see that?
Yes.
That's the simplicity of mathematics. That's what I want you to see. That's why I make this theme. It's a function. Just we study about their input output. Two kinds of statements, statement, if statement. That's all. That is all. And of course, for each different rule, you get different features. Okay, so you're gonna see this theme played out over and over again. So that's why I hope you to see. Okay, because I present this course this way. So you see simplicity, you see consistency. All right? Okay, so let's make the wording. Let's make the wording. Okay, this is the increasing function, right? Whenever is smaller than x2, whenever the input x1 is smaller than x2, two to the power of x1. Last time we did not equal to, right? That's a one-to-one function, isn't it? So now it's about increasing function. That is f of x1. F of x1 is smaller than f of x2. And then what you say? F of x equals 2 to the power x is increasing in its domain. Because this statement is true everywhere. Do you follow me? It's increasing. So sometimes for this function, we can say it's increasing because it's increasing everywhere. Do you follow me? Next, we're going to talk about log base 2x. Log base 2x. Did you write it down? Has it become easier? Has it become easier?
Yes.
You should see consistency. You should see consistency, right? All these descriptions I've put in here, I'm repeating myself over and over again for different rules. Okay, wait. So now can you make a similar statement about log base 2? Is log base 2x increasing? And after this, we're gonna jump to e to the power x and ln x. Okay. This is how you speak the language of mathematics. Okay, that's how you speak the language. You write the language, okay, of mathematics. Because in this language, for any language, right? For the language of Spanish, you have reading, writing, and what else? Reading, writing, speaking, right? In the language of English, you have reading, writing, speaking. Oh, there's a listening too, right? Sorry, I forgot. Because I don't teach language art, right? Okay. For any language, you have reading, writing, listening, speaking, right? For math, same thing. Reading, writing, speaking, listening.
Professor, I have a question.
Yes.
Say for example, if we have that same exact statement, but just didn't put the 2 to the power of x1 less than 2 to the power of x2, would it be incorrect? We have to restate x1.
How about you just do exactly what I do here to ensure you get all the points? Why does that bother you? Huh? You want to make it the most obvious to the reader, to your grader, so that she will give you all the points. How do you don't like that? You don't like that fact? A lot of the conclusions is drawn because you pointed out the most obvious. You follow me? What I'm showing you my best. I was a student before. I did my best I can. I wasn't a straight A student. You know, I got some A minus, and sometimes I even got a C. But I give my best. I teach this class, I give my best. This is the best statement I want to make in front of you. If you want to cut corners, that's your choice. Don't ask me how many points I'm going to cut, because I don't know. In that situation, I might decide if everybody do the same thing, I decided to cut 1 point. You follow me? I always get these kind of questions, okay? I show them work like this, and student will come back to ask me, how about I remove this word? I take away that word, and I chop this down. I don't know how to answer that question. I cannot tell you how many points I will not give you. But I can only tell you this work I show here is the best work I can do. Is that good enough answer for you? And some people, you can even say, oh, this is very easy. Yes, it's very easy. Then do it. It's not hard. I really want to tell you, this stuff you're learning here is not hard. Do you agree it's not hard anymore? I want to make this class simple, easy, and yet you get all the points. And you see consistency, and you see simplicity. That's all I wanted. I didn't want to make it hard for you. I didn't want to make you do extra work. You hear me? All right. So let's look at log base 2x. I'm sorry, I was a little abrupt. I have received too many questions and students cut corners here and there. It's like you build a house. It's, oh, can I remove this beam? Well, maybe it's okay. It's not going to fall, right? Maybe, I don't know. But the engineers, when they design those houses, they always probably put sometimes unnecessary beams to ensure the safety, isn't it? I'm sure, you know, they don't put minimum number of beams for a particular construction. And I wouldn't feel safe. Okay, so don't try to cut corners. Okay, don't try to cut corners. All right, so let's look at the next function. I want you to understand, I make this effort. I type every word on the screen because I want to ensure everything is clear to you. I have decent handwriting. I could write it. I can. One day you come to my classroom in the, you know, on campus, you see my handwriting on the board is very decent. But I still want to give you the most clear version of how to and what to do. Okay, so now, log base 2x. Can you make a similar statement? Of course, that has to be true, right? It has to be true. And you look at the graph. You look at the graph. Right? And we know this domain, we have discussed all of that. And this time, when you make the statement, you have to be aware of the domain because this function is increasing in the entire domain. Okay, this function is increasing in the entire domain, which is, what is it? From 0 to infinity. From 0 to infinity. Okay, and so if you go over this again, which I, you know, so input 1, input 2, right? And what are their output? This is output 1, output 2. For any inputs, x1 is less than x2, f of x1 is always smaller than f of x2. Okay, I know most of you are not used to this. That's why the transition to calculus class is so difficult. So difficult, very difficult. It was difficult for me as well. Okay, 30 years ago. Wait, how many years? About 40 years ago. I'm that old. Okay. A lot of these things I'm giving you tips as how to success in calculus class because I have struggled much. I've struggled much. Okay. Now, whenever, are you done? X sub 1 is less than X sub 2. But you also have to tell the reader X sub 1, comma, X sub 2 are from the domain, which is 0 to positive infinity. You have to specify these. You have to specify these. If you don't, you're in calculus class, you may lose a point. Sorry. Okay, but as long as you touch these few places, then you're good. Okay, so then log base 2x1 sub 1 is going to be less than log base 2 sub x2. That is f of x. Well, I'm using this notation, okay? So I'm gonna be consistent with this notation. So f of x sub x1 is gonna be less than sub x2. Then you can say thus f of x, f inverse x equals to log base 2 x is an increasing function. Okay, the wording is a little bit different because sometimes I say it's increasing, and where is it increasing? In its domain. In its domain. All right, so we have done so much for 2 to the power x log base 2x. And the next one, the next biggie is number 11, 12, e to the power x and ln x. Everything we do for log base 2, for e to the power x and log base 2x, I'm sorry, they can be applied to these two functions. Okay, so let's go back to the top. Okay, the function equal, which is e to the power x. And the other function is ln x. Okay, so I'm going to call it G. Okay, you're going to see a lot of these two functions. You're going to see these two functions used a lot in calculus class. Okay, so how are you going to plot it? I believe most of you have never plotted them, have never graphed them. Is that true? Oh, sorry, I forgot to look at the chat. Do we need to make a claim like we did for x? I'm sorry, Aaron, I didn't see this question. Do we need to make a claim like we did for x squared? I don't know which function you refer to. X squared, you see these statements you make here, they're often incomplete. I hope I have answered those questions in the process. Have I? I forgot to look at
I noticed for the decreasing function, for x squared, we stated that f of x equals x squared is decreasing, and then we said because. So I was wondering if we needed to do that for like increasing and the other ones.
You have to tell the reader where it increases, where it decreases. For example, if you make a blunt statement saying x squared is decreasing, false, you get 0. Okay? There are only two kinds of sentences in mathematics: statement, if statement. If the statement is wrong, you get 0. There's no like the statement is sometimes right, sometimes wrong. It's either completely right or completely wrong. So when you speak for x squared, I thought we explained this. Okay, x squared, what did we say? X squared is increasing here, decreasing here. Is that clear?
Yes.
Okay, that's how you say it, to ensure your statement is perfect. Do you follow me? Because for example, if I read your statement, I say, you write that statement and say, oh, x squared is increasing. You get 0 because x squared is not increasing. You didn't mention where, so by default, I will consider the entire domain. And then you say, oh, x squared is decreasing. Wrong, you get 0. Do you follow me? Do you want me to write it down for you?
Yeah, I'm just confused because we didn't do that for log. And
what do you mean we didn't do that for log?
Well, we didn't make the claim. We just went straight to whenever.
We didn't do it for log. It's right here. Log base 2x is an increasing function in its domain. Did you see it here? Yeah, do you see it here? Log base 2x is an increasing function in its domain.
So I guess for x squared, you just put it twice because you said in the beginning f of x squared or f of x equals x squared is decreasing, and then you went to whenever, but for log, you just said whenever, and then you put it at the end.
I don't know what you're talking about. Can you go slowly? For x squared, okay, let me write it down for you. F of x is increasing in the interval zero to infinity. That's a statement you make. But if you remove this, so this is true, and this is a false. I said that. Okay, you can go back to the lecture to see it. Is that clear? Okay?
Yeah.
Now, f of x equals x squared is decreasing negative infinity to 0. But if you say f of x squared is decreasing, that's false. So here, you're gonna get all the credit, and here you're gonna get 0. If you make a false statement, you get 0. Do you follow me? If your sentence is incomplete, and as a result is false, you get 0. Do you follow me? Yeah, that's what I'm trying to say. Studying mathematics is a training. I really think it's a training. A training that is gonna be helpful for you with any career. Okay, do you see the difference? This is true because I tell where, and it is true. If I didn't say the where, okay? By default, the reader will consider the entire domain. And that is not true because we say this function is neither increasing or decreasing in domain, okay? F of x is neither increasing nor decreasing in the domain, in its domain. All right, any other questions, please? I'd be happy to, clarify for you. Yeah, is that clear? If you have a question, you can private message me, or you can just type the question on chat. If you're a little embarrassed to speak in front of everyone, and then you can private message me. I will do my best. I will do my very best, because I think you deserve nothing but my best. Okay. So how about log base 2? Do you need to clarify about log base 2? Right? So I can say f of x, 2 to the power x is increasing in its domain. In its domain. Do you follow me? Okay, log base 2 x is also increasing in its domain. I'll tell the reader where. I tell the reader where. If there's a pieces, and I will specify each pieces, that's what you will need to do in Calculus 1, Chapter 4. Okay? I'm seriously preparing you for calculus class. A lot of the exercise I put in here, they're same questions from your calculus class. I take out those questions from textbook, from calculus textbook.
I have a question.
Yeah.
For f of x equals 2 to the power of x and f of x equals log base 2x, do we have to state the domain in interval notation, or can we just say it's just increasing in its domain like you just did?
You don't need to, but you know it, right?
Yeah.
Okay. So if you ask, you know how to do it, right?
Yeah.
Oh, you can also say it's increasing for all real number. There are all these different ways to saying it, okay? You know what I mean? There's so many ways to say it. There's so many ways to say the right thing. For example, you see a lot of exercise on your quiz questions, right? I give you a lot of quiz questions and ask you to choose all the correct answers, not just pick out the single one. You will see a lot of these kind of exercise in your quizzes in the future, on your exams, midterm, final. Why? Because there are all these different ways of saying it, and you have to be able to understand each one of them to be successful. In fact, this semester, I'm glad you asked this question. This semester, I will put a lot of emphasis on using inequalities, because that's the weak point of our student, all the student. 99.99% of our students are weak at using inequality. And a lot of them can use interval, right? Therefore, because I want to help you, right? I want to help you. So I'm not going to encourage you to use more interval if I know you already know how to do it. I want to show you how to use inequalities, because that's the weak point of all the students. I'm not just talking about El Camino College student. I'm talking about student at USC. I'm talking about student from Cal State, UC. All of the students, they're not very good at using inequalities, but yet using inequalities is very important for your success in math classes. So that's going to be the new emphasis. You'll find me telling you that, you know, if you give this answer in interval form, you're not getting point. You're getting point for giving the inequality form. Do you follow me? So you learn new things and you'll be rewarded for what you have learned. All right, so that's a long story. We're getting to the end of the class, but I really want to get started on e to the power x and ln x, because these two functions are two functions that you're going to use a lot in calculus. In calculus class, you're not going to be using these two functions very much. But why did we spend so much time here? Because they're simple. Okay, so now let's do it. Let's do it. Graph. Okay. I have assumed none of you have graphed this one. Am I right? Forgive me.
Doesn't it look almost like the it's basically the inverse of the, what is it called? The log, right? So it'd just be the exact opposite.
Which log?
The log function.
Which log function?
Log base 2.
Are you saying e to the power x is inverse function of a log base 2?
Yeah.
Wrong. Wrong.
It's 10. It's 10.
It's wrong.
Log 10.
No.
No.
These two are inverse function to each other.
Oh, okay.
Okay? 2 to the power x and log base 2x, they're inverse to each other.
Okay.
Okay, thank you for speaking up. These two functions are inverse function to each other. We talked about this last time. Okay, so please go back to watch those lectures. Are inverse to each other. What we're doing here is called analytical geometry. Analytical geometry. I have discussed these issues with professors who teaches in 4-year school. We both agree our student needs some more groundwork for it. Okay, I know some of you are going to transfer to USC, CSU, UCs, maybe even out of state. This is an issue nationwide, and maybe even international wide. Okay, so be patient with me, just do the work, okay? We're trying to build something on a rock. Okay, so let's make the point. Let's plot this. Everyone have paper, pencil, please? Paper, pencil, please. Very good. All right. Input. The first question about e to the power x is, what is e? What is e to you? What is e to you? Everybody. Could anybody tell me what is e to you?
Isn't it 2.71?
Very good. Actually, you only give.
Well, it's ongoing, but like.
I know, you're right. There are infinite number of numbers, the infinite number of digits afterwards. Why is this number so important? Why calculus use only e to the power x ln x? This number looks so unusual. It's weird, isn't it? And why? There's a book written about E. Actually, I used to have that book on my shelf. Maybe I moved to the other shelf. And I usually put it here for my convenience so I can show it to you. So when I need it, I couldn't find it. But anyway, E turn out to have something to do with finance. With money. Okay, it has a lot to do with a lot of natural phenomena. Okay, it's a very useful number. So E is a constant. E is a constant. Okay, so E is, if I want to show you, I only get one more digit, right? So Gordon's answer is just as good as mine, because there are infinite number of digits. It's an irrational number. It's an irrational number. But anyway, but we treat it as a constant. We treat it as a constant. You see, this symbol is so important. Okay, this symbol is so important. In the entire field of mathematics, this letter E is reserved only for this number. This letter E usually is not used for anything else. If you go through all the textbooks, in mathematical textbooks, you never see E is being used for something else. So this number is so important, so powerful. Okay, mathematics reserve one symbol for it, just like pi. But pi is outside the 26 letters, right? But E, we take one letter out of 26 letters and reserve this letter for this number only. Do you guys follow me? That's how important this number is. And I also tell the other, people it tells everybody in the field of mathematics or in science, and say, hey guys, we use E only for this number. Please don't use E for anything else. Do you get me? Okay, so Kyle says, is E not a one-to-one function since it's a constant? Very good question. E is just a constant. E is just a number. So when you think of E, you think of E just a number. You think of E as a 2.718 and so on and so forth. It's just a number. It's a constant. It has nothing to do with one-to-one function. Do you follow me? Because a one-to-one function is a rule. A function is a rule. E is not a rule. It's a constant. You follow me? So E treated as a constant. And sometimes you might need to use this fact, okay? 2 less than E less than 3. So E is a number between 2 and 3. You actually don't need to know its actual value unless you do calculation. Okay, in calculus class, you're gonna learn different forms of expressing E. Okay, so E is very, very useful, very, very useful. Or you wanna get all the points, you wanna get your grades, get your requirement finished, get your degrees, you have to get over this. You have to get over this. Okay, so I'm just gonna show you how you get over this. Because it's a constant, so it has a similar role as 2 or 3. Do you follow me? So just like a domain for 2 to the power x, the domain for E to the power x is all real numbers. Is that understandable? Negative infinity to positive infinity. So now we're gonna plot it. We're gonna plot it. And I'm gonna put the question right here. Tell me what's the range.
All real numbers greater than 0.
Perfect. Perfect answer. Okay, all real numbers greater than 0. But this answer is not enough. Okay, we have a one sentence domain range statement, which is e to the power x is larger than 0 for any real number. This sentence is super duper useful, super duper useful. So another version for range is e to the power x larger than 0. This is a preferred version. And this is the words to understand. And this is its translation. When you operate in mathematical expressions, among them equations and so on and so forth, and this latter one turned out to be very, very useful. But it really means the same thing as you just, that lady just stated. Okay, all real numbers greater than 0.
And why would you say for any real number x?
Because I'm specifying the x.
Oh, okay. And then like the x has to be greater than 0, so that's what it basically means.
What do you mean? X is all real numbers. This is always a positive. This is basically say e to the power x is always a positive.
Okay, okay.
Okay, there's so many ways to say it, you see? And each way is to enhance our understanding. Each way is enhance our understanding. Do you follow me? Well, you can also say e to the power x is always positive. No matter, you can even say, no matter what x is. Okay. Another way of, another thing that you're going to learn that you need to, is whenever you have something in your expression, you need to specify every variable. You need to specify every variable. Okay, when we get there, I will show you. For example, here is an example, right? Someone just asked me, why you for any real number x? Because I'm referring to this unknown. E is known, but x is unknown. I'm specifying what kind of unknown could this be? Do you follow me? Do you follow me? Okay, so now I want you guys to plot these points. Actually, our time is up. Okay, today's homework. Okay, today's homework. I want you guys to plot these points for E and ln. ln x. For ln x, okay, we also have input, output, so on and so forth. Input -1, input 0, input (1 over e squared). Write it down, please. Input 1 over e. Input 1. Okay, that's your homework. Okay, you're gonna fill up all the outputs, points. And I also want you to compare the way I did it here. We did it here with what we did with 2 to the power x and log base 2x. Do a comparison. And then you plot the points and connect the dots. Could you follow me? That's your homework for today. Compare with what we did for 2 to the power x log base 2x. And that's all for today. I'm sorry I'm late for office hours, but I appreciate all the participation, all the questions, big or small, okay? And I'll see you guys tomorrow. Okay, so this is your homework. This is your homework. Okay, I'll see you tomorrow.
Thank you, Professor. Have a good day.
You too, very good job.
Have a great day, Professor.
Very good job, okay? Do it by your own hands on your paper pencil, okay? Only when you do this, the knowledge you learned is yours. No one can take it away from you. Okay? Namaste. I will see you guys tomorrow. Thank you, Lynn. Thank you, Kim. I'm sorry I hold you guys up. Thank you.
I have a question.
Yes.
For the quiz, is it going to be based on this lecture and yesterday's lecture, or just this lecture?
Is it going to be based on all the lectures in the past?
Oh, okay. So, okay.
Yeah, I cannot pinpoint. I'm going to base on only this lecture or the 2 lectures before. Everything covered before may be covered by quizzes.
And is that quiz supposed to be up yet? Because I don't see it on campus.
Oh, did I give you the, oh, let's see. Let me check. I told you, oh, I'm sorry. Thank you so much. I'm gonna publish it. I just published it. I'm sorry you didn't see it. And I'm gonna make it a little longer. Sorry about that. The quiz actually was about what we covered before today. My bad.
Okay.
My bad. Thank you for reminding me. It is totally my mistake.
No worries. Okay, now I can see it.
Thank you. Thank you.
All right. Thank you.
Thank you.
Have a good day.
You too.